Does your favorite sports team win more often when you wear your lucky socks? That depends on whether wearing the socks and winning are independent events. And that's what we are going to talk about today. In probability, we call the sample space the set of all possible outcomes. An event is some set of outcomes in the sample space. So if you think of rolling a die, rolling a 5 would be an event, and the sample space would be the numbers 1 through 6, as those are all the possible numbers you could roll. So what are independent events? These are events that have no effect on each other, like rolling a die and flipping a coin. The die does not affect the coin and vice versa. If two events did have an effect on each other, such as a product's price affecting how many customers buy it, then they would be dependent events. But in some cases, it's not obvious whether one event affects another. So how do we tell if two events are independent? Well, we can use their probabilities. Events A and B are independent if and only if the probability of A and B both occurring is equal to the probability that event A occurs times the probability that event B occurs. Great! Let's practice identifying independent events in some examples. Let's say that you tested that sock theory with an experiment. For each game played by your favorite sports team, you kept track of whether you wore lucky socks or not, and whether the team won or lost. Using that, you calculated the following probabilities. You have a 1/5 probability of wearing your lucky socks, and your team has a 1/2 chance of winning. Also, there's a 1/10 chance that both occur. Are wearing your lucky socks and your team winning independent events? Let's look at a diagram to help us think through what's going on. Your team won half of their games because the overall probability of winning was 1/2. Now let's split the games based on whether you wore your lucky socks or not. 1/5 of the games were with lucky socks, and 1/10 of the games were won while wearing your lucky socks. If the events are independent, your team should still win half of the games they play while you're wearing your socks. That's 1/2 of 1/5, or 1/2 times 1/5, which is 1/10. So the fraction of total games won while wearing your lucky socks would be 1/10. Since 1/10 matches the probability from the experiment of both events occurring, these events are independent. So that's where this formula comes from. So what does it mean that these events are independent? Well, unfortunately, it means that wearing your lucky socks does not help your team win. What would it look like if these events were not independent? Well, if wearing your lucky socks does help the team win more often, then the diagram would look more like this. Great! Let's try another example. Here we aren't given the probabilities, but don't worry, we can still figure out what we need. Let's try it. Sebastian is shopping for a new shirt. He is most interested in the color and the price, as shown in the table. Are the events the shirt is blue and the shirt costs less than $25 independent? In order to see if these events are independent, we need to calculate the probability of each event and then the probability that both events occur. Let's say event A is the shirt is blue. So to find the probability, we need the number of blue shirts over the total number of shirts. There are 15 blue shirts in all, 12 that are less than $25 and 3 that are more. And there are 12 plus 4 plus 3 plus 1, or 20 total shirts. So that means the probability that the shirt is blue is 15 over 20, or 3 over 4. Now let's let event B be the shirt costs less than $25. There are still 20 total shirts, and 16 of them are under $25. These 12 blue ones and these 4 red ones. So the probability that the shirt is under $25 is 16 over 20, or 4 over 5. Okay, so what is the probability that the shirt is both blue and under $25? Well, there are 12 such shirts and 20 total shirts, so that's 12 over 20, or 3 over 5. So now we just need to check if the probability of A and B is equal to the probability of A times the probability of B. 3 over 4 times 4 over 5 is 12 over 20, which reduces to 3 over 5. So yes, these events are independent. So what does it mean that these events are independent? Well, it tells us that the color of the shirt has no bearing on the price, and vice versa. So blue shirts aren't any cheaper or more expensive than other color shirts. Let's do one more example. Olive is observing the animals that visit her garden during the day and at night. This table shows the data she collected. Are the events the animal is a mouse and the animal visited at night independent? Remember that in order to see if these events are independent, we need to calculate the probability of each event and then the probability that both events occur. Let's say event A is the animal is a mouse. So to find the probability, we need the number of mice over the total number of animals. There are 8 total mice, 1 observed in the day and 7 observed at night, and there are 1 plus 7 plus 5 plus 5 plus 10 plus 2 total animals, which is 30 total animals. So that means the probability that the animal is a mouse is 8 over 30, or 4 over 15. Now let's let event B be the animal visited at night. There are still 30 total animals, and 7 plus 5 plus 2, or 14 of them, were observed at night. So the probability that the animal visited at night is 14 over 30, or 7 over 15. Awesome! So what is the probability that the animal is both a mouse and visited at night? Well, there were 7 mice observed at night out of 30 total animals, so that's 7 over 30. So now we just need to check if the probability of A and B is equal to the probability of A times the probability of B. Well, 4 over 15 times 7 over 15 equals 28 over 225, which does not equal 7 over 30. So that means that these events are not independent. This tells us that the probability of the animal being a mouse and the probability of an animal visiting at night affect each other. Why might this be the case? Well, mice are nocturnal, so it makes sense that they would be more likely to visit at night. Wow, awesome job! Now you know how to determine if two events are independent.